digital electronics are nothing but if we consider any electronic devices, the building blocks will be the digital circuit. So for that, we have to go through the digital electronics. We should understand what it is and why we need it. So in that, like first we'll come to the logic gates. So what are the logic gates? The logic gates will be the building blocks of any digital circuit. You take anything like whatever, like adders, subtractors, sequential circuit, what it will be made up of. So it will be made up of the logic gates. If you consider the same thing, like if you have a wall, so the wall will be constructed based upon the bricks, right? So in the similar way, the logic gates are like a bricks, nothing but those are a sorry, building blocks of any digital circuit that will perform the operation, any logical operations, so which will be required for your digital circuit. It may have the one or two or many inputs, but it will give only one output. So in the logic gates we do have a categories like a basic logic gates, universal logic gates, and other logic gates, or else you can say it as a arithmetic logic gates. So what are the components or the gates which will come under the basic gates? In the basic logic gates, we'll have NOT gate, AND gate, and OR gate. Why we'll call NOT, and OR are the basic logic gates? It means that whatever you take the universal gates or the logic gates, it will be made up of these three gates only, basically. So that is why these are called the basic logical gates. Next will come for the universal logic gates. The universal logic gates are NAND and NOR. Why we are calling universal logic gates are the NAND and the NOR? Why? Because with the help of NAND and NOR gate, you can implement any gate. Either it may be the AND gate, NOR gate, NOT gate, XOR, XNOR. Anything you can implement with the help of the NAND gate or the NOR gate. So that's why it's called as a universal logic gates. Next will come as a other logic gates. In other categories, the XOR and XNOR will come. So the XOR and XNOR, you can either call it as a arithmetic logic gates. Why? Because with the help of the XOR and the XNOR, you can do the arithmetic operation. So we'll see one by one what are the types of the logic gates. So here you can see that NOT gate. So the NOT gate, it will be having only one input and one output. Here you can see. Just a minute. This is the symbol of the NOT gate. This is a symbol of NOT gate. It will be having one input and it will be having one output. So how does it operates? Whatever you are giving the input, it will give the inverted of that input. Suppose if you are giving input as a 1, it will give output as a 0. So it will be having one input and it will be having one output. Its operation is, it will be in whatever you will give the input, it will be providing the inverted of that. So here you can see that the truth table. The truth table is nothing but it will be having the inputs and the outputs. So the inputs you will be having the combinations, like if you have the one input, it will be having the, if you have the one input means the possible conditions, either it might be 0 or it might be the 1. So with respect to that, it will be providing the output. The truth table is nothing but it will be having all possible conditions of inputs and the outputs. So here the input is A and the input you are providing as 0. So here, if you provide the input as 0, it will give the inverted and you will get the output as 1. So that is why it will be represented as A bar. So here, so if you give the input as 1, you will get the inverted. So the output will be 0. So whatever you are giving the input, it will be having the inverted of that. So this is the NOT gate. Next will be the AND gate. So the AND gate, it will be having a 2 or more inputs. It will provide the only one output. So the operation of the AND gate is, it will do the logical multiplication. Suppose consider that you have, this is the symbol of the AND gate, and this is a two inputs A and the B, and this is the output is Y. So here, if you are providing the input as a 0 and output as a 0, and it will do the multiplication operation. So you will get as 0 into 0. So here you can see that in the truth table, with respect to that, you will be having the two inputs. It means that if you have the two inputs, how many combinations you will be having? If you have a two inputs, so how many combinations you will be having, like a possible combinations?
Four
Four.
combinations.
Four
Four.
combinations. Yes, four combinations. Four combinations might be the 0, 0, 0, 1, 1, 0, 1, 1. So here you can see that input A is 0, B is 0. 0 into 0 is equals to 0. 0, next A is 0, B is 1, and 0 into 1, it will be 0. A is 1, B is 0. Here you can see that. 1 into 0, it will be 0. A is 1, B is 1. So here you will be getting the AB as 1. So whenever you will write the expression, so whenever you have the output as a 1, you will write the expression. So here A is 1, B is 1, you are getting the Y is 1. So here you can see that this will be the operation. Y is 1. So here A is 1, it means that it will be A. B is 1, it will be B. So whenever, yeah, either way you can write it as A dot B, because it is doing the logical multiplication operation. Can anyone say that what is the application of the AND gate? What are the applications? Why we need the AND gate? Why
If
we need
both
the, yeah.
if both condition true, then only it will execute. Same
Yeah,
answer.
yeah, I got it. Like what you were saying, whatever you were saying, that's a operation, right? So I'm asking, what is the application? Why we need the AND gate? AND gate will operate when both are at a high, nothing but it will give the result only once the inputs will be, both the inputs will be available. So what are the applications in real time where you can see the application?
For multiplication.
For multiplication, okay. In real time, okay. I think
When
okay.
both inputs are high,
Hmm.
it is only the application of AND gate. Then output will be high only.
See, just the operation of the AND gate is like it will do the logical multiplication. So it will be providing both the inputs, whatever you are saying, right? It will give the output whenever both the inputs are high. So it is not like that, like it is providing only output when both are at a high. Suppose consider that here A input is 1, B is 0. It is giving the output as a 0. 0 is also output. It is giving that whatever you are providing, that is 0. 0 is also output. If either 0 or the 1, it's a output. But I am saying like in the real time, suppose consider that you are sending the data. Okay, in the data transmission, you can use the AND gate. So suppose consider that in a both transmission line, you are sending the data. If you are sending the data in one transmission line, in other transmission line, the data has corrupted. So this is a one line and this is another line. This will be, suppose consider this is a AND gate. And this here you should send the data. Okay, this will be Y. Suppose this is A and this is B. Here I am sending the data as, suppose consider that whatever it is a PD, here I am sending the data. So the PD is a data, here I am sending the P and here I am sending the D. So it should detect the signals both A, P and D, and here it should get P, D. Suppose consider that here instead of D, you are not getting the D. So here you won't receive the PD as a data here. Because in the one transmission line, you are getting the data, and other transmission, you are not getting any data. So that's why we use the AND gate. It is just a one example. In many applications, you can see the AND gate. Next will be the OR gate. So OR gate, it will be having a two or more inputs and it will be providing one output. So, but here, sorry, I forgot to mention in AND gate also, the AND gate should have at least one input. Both like, at least it should have two inputs. If we have only one input in an AND gate, it will work as a NOT gate or the buffer, whatever it is. The OR gate, it is having a two inputs or more than two inputs and it will be providing only one output. The operation of the OR gate is it will do the logical addition. So here you can see that this is a OR gate symbol. It is having a two inputs, A and the B. Y is the output. And here you can see that in the truth table, there are two inputs, A and the B. So since we do have a two inputs, you will be having a four possible condition, 0, 0, 0, 1, 1, 0, 1, 1. So 0 plus 0, it will be 0. 0 plus 1, it will be 1. 1 plus 0 will be 1. 1 plus 1 will be 1. So that's why we call it as a logical addition operation. The operation of the OR gate is logical operation. So it means that it will give the output when any one of the input is at a high. So it will provide the output. So that's why this is the expression. So what are the OR gate application? So nothing but the operation of the OR gate is like out of two inputs. If any one of the input is at a high, it will provide the output as at high. If both the inputs are low, the output will providing the low. So where you can see the real-time application.
Fault analysis and correction in digital logics.
Okay, yeah.
Microprocessors and controllers.
Yeah. See, as you say, like microprocessor and controller, right? If you take any digital circuit, the basic aids will be using. So that will be the one of the application. So I am asking, like, as you said, like a false controller, right? I don't know, like someone said that the controller OR gate will be used, right? Okay. In the same way, like in the false controller, in the alarm circuits, in the sensors, or in the trial room display, in the mall. So there the OR gate applications can be used. Suppose consider that you have a 3 trial rooms in the mall. So just for the example, I'm saying this will be the 1, this will be the 2, and this will be the 3. So out of 3 trial rooms, if any one of the trial room is vacant, if the people are waiting outside, right, so they should know, like, any one of the trial room is vacant, they can go and they can trial, right? So it, for that it should show like a vacant, right? So here if you are providing the input, like if you use the 3 OR gate input here, for example, I'm saying if any one of the input is a vacant, it will show output as 1. So the people will go and make trial, do the trial, right? So here they can use the OR gate application. Any doubt so far?
No, ma'am, no doubt.
Okay. Next will be the arithmetic gates, nothing but the XOR gate. So the XOR are nothing but exclusive OR gate, which will be having a 2 inputs and which will be providing the only 1 output. So here this is the symbol. This is the symbol of the XOR gate, or else you can, this is the symbol. Both are same. So here it will be having the 2 inputs. If we have the 2 inputs, it will be providing the, sorry, it will be having a 4 possible condition. What are the 4 possible condition? 0, 0, 0, 1, 1, 0, 1, 1. The operation of the XOR is it will provide the output whenever only one input is high at a time. Suppose consider that you have the A and the B as a input, and this will be your Y. So when input is 0, output is 0, it won't provide the output will be 0. So the input will be 0, another input is 1, so it will provide the output as 1. Similarly, the input is A is 1, another input is 0, it will provide the output as 1. If one input is A1, another B input is 1, it will provide the output as 0. The output will be high whenever any one of the input is high. So here we are writing the expression. This will be Y is equals to, here we are writing the expression is whenever the output is at a high. So with respect to that, what is A? A is 0 here. So this will be A bar, and B is 1. So it will be B plus, and the plus is nothing but we are taking one more term. So that's why we are adding the plus. We will discuss like how to write the expression in the next session. So don't worry about that. And A is, this will be A is 1. So this will be A, and B is 0. This will be B bar. So here you can see the expression as A bar B plus B into A bar. So what are the applications of XOR gate? What are the applications where you can see the real-time application?
Timers.
Sorry? Sorry, I didn't get like what is the application?
Timers, like the timers.
Timers, nothing but like you are counting purpose you were saying, or
Yes,
else
yes, counters and timer circuits. Like washing machines. Like.
they we will be using the just you are adding one thing, right? In the count timers, it is counting the times, right? In the arithmetic, you can heard about the error correction method, sorry, error detection.
Yes, ma'am.
So yeah, for the error detection, you can use the XOR gates.
Or ma'am, for converting binary code into gray code.
Yeah, that is a XOR operation, right? Whatever you are doing the from the binary to gray code converter, for that you will be using the XOR operation. Any doubt in that? Like in this one?
Error detection, that
Sorry? Like you are saying like how the XOR gate will be used in error detection.
yes ma'am.
Okay. Suppose consider that you have a file is a like whatever you are sending the data. Like suppose you are sending the data as a A, it means that you should get the another like you should receive it as a, right? Whatever you are sending, that should whatever you have received, both should be the same, right?
Yes ma'am.
So in this case, you should not get any error. Why? Because whatever you have sent, you have received. Suppose consider that you have sent the data as a, but you have received the data as a B. But if you don't get any information like whatever I have sent, whatever the person has received, it should be the it won't be the same. Suppose consider that you have sent the data and you have sent it as a, but whatever they have received it is a B. But if they have received it as a B, you should get a notification that okay, these guys have received this as a B. So for that you should get the notification, right? That will be the error. So here you can see that in the truth table itself, this will be like a, you are not getting any error. This will be like a and this will be like a B. You will get as the detection or the pop-up or the notification, this whatever the data which is not correct.
Okay ma'am.
Okay. Any doubts? Okay. Next will be the XNOR gate. So the XNOR gate, it's a exclusively NOR gate. So it will need the it needs two inputs and it will provide the only one output. It is nothing but like inverted of XOR operation. So here either the symbol is, you can do this symbol. This will be the XOR symbol, nothing but this is a XOR operation, right? And this will be inverted of this one. This is A and this is B and this will be Y. So here you can see that this will be A XOR B and this whatever you will get the output here, you will get the implemented of this one. Suppose consider that A is a 0 and B is 0. What is the operation of XOR? When A is 1, B is 1. For the XOR
1.
operation, when A is 0,
0.
B is 0, what you will get at the output?
0.
For the XOR,
0.
0.
For XOR 0.
For XOR, it will be 0. Since it's
Same
a
inputs
XOR,
0,
it
different
will be,
inputs.
it will give the inverted, it will be 1. So when you have the 0 and the 1, for the XOR, you will get it as a 1. For the XNOR, it will be inverted, you will get it as a 0. Similarly, when it is having a 1, 0, for the XOR, you will be having, what is the output? 1, right? So 1 will be inverted, it will be having a 0. So 1, both the inputs are at a high, the XOR will be 0 and XNOR will be 1. So it is an inverted of XOR operation, or in a simple manner, you can see that whenever both the inputs are at a same condition, you will be having a output at a high. So when both the inputs, like the changes, like A is 0, B is 1. So the condition is like both the inputs should be low or both the inputs should be high. So when both the inputs are at a low, low is nothing but it's a 0. High is nothing but it's 1. So when both the inputs are at a low, it gives the output as a high. When both the inputs are at a high, the output will be high. If there is a condition like if any one of the input is low, the output will be low. So the low, it indicates the bar, like A bar. High will be indicates as a A. So here you can see that the output is at a high. The output is at a high. It is 0, A bar, B bar. So it will be A bar, B bar. This A is 1, B is 1. So the output will be 1. Nothing but A into B. So here there are two terms. So that's why we are adding it as a operation. Sorry, plus. You can also symbol it as A XNOR B. Like circle, within a circle, it's a dot. This is the symbol of XNOR gate. This will be the XNOR gate symbol. Nothing but in the expression. In such a way that instead of writing this thing, you can also write the expression as A XNOR B. Any doubt? Any doubt? Okay. What are the applications? What are the real-time applications?
Adders, subtraction.
Adder, subtraction, okay. Apart from that, yeah, that is correct. Whatever you guys say, like adders and subtractions, the XNOR, it will be used in the subtraction. See, it is not only in the subtraction, wherever the arithmetic
Parity checker.
operation is right. Sorry? Yeah. The parity checker also you can
See, it
use
is
the
not
XNOR.
only the subtraction, wherever the arithmetic operation.
Yeah. I think you guys have unmuted. Yeah. In the parity checker also you can use the XOR gate, and wherever you want to check the data, right, there also you guys can use the XOR gate. Next comes to universal gates. In the universal gates we have the NAND gate and the NOR gate. Why we are calling NAND gate and the NOR gate are the universal gates? Why? Because you can implement any gate with the help of the NAND gate. Whether you can implement AND gate, NOR gate, XOR gate, XNOR gate, NOT gate. You can implement any type of gate with the help of the NAND and the NOR. So that is why these two gates are called as a universal gates. So for this NAND gate, you should have at least two minimum inputs, and you will be getting only one output. So here, this is a symbol of the NAND gate, or else you can see this is a explanation of NAND gate. So here you will be having two inputs. So if you have the two inputs, it means that you will be having four possible conditions. Sorry, four possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. Here you can see that what is the output when you are having two inputs are at a low. What is the output when both the inputs are at a low? 0. So here the output of the AND gate is 0. The input of the inverter is 0. If the input of the inverter is 0, the output will become
1.
1. So when both the inputs are at 0, you will get the output as 1. So here you can see that A is 0, B is 0, output is 1. Next condition, A is 0, B is 1. A is 0, B is 1. 0 into 1, it will be
0.
0 into, yes, 0 into 1, it will be 0. 0 inverted will be the
1.
1. So you are getting the output as 1. So when A is 0, B is 1, the output will be 1. Next possible condition is A is 1, B is 0. A is 1, B is 0. So 1 into 0, you will be having the output of the AND gate will be
0.
0. The 0 input is to the inverter. So what will be the output?
1.
1. So the input is 1. The A is nothing but one of the input is 1 and another input is 0. So you will be having the output as 1. Next, A is 1. Both the inputs are at a high now. A is 1, B is 1. So what is the output of the AND gate when both the inputs are at a high condition?
Output is also high.
High, right? So here the output is high. This is input to the inverter. So what could be the output here?
Low.
Low. 0. So here you will be getting the output as 0. So in the NAND gate, if you see that this is exactly opposite to the AND gate, right? So in the AND gate, the output will be high when both the inputs are at a high. So in the NAND gate, it is like when both the inputs are at a high, the output will be low. So this will be exactly right. This is the AND gate expression. So this you can write it as a NAND gate. Why? Because this will be the inverted of the NAND gate. So you can write the expression as like this. What are the applications of universal gates? Either it may be the NAND gate and the NOR gate. What are the applications? What are the applications? Why we need it?
It is used in flip flop and latches to store the data.
To store the data, you need the NAND gate.
Used to store the data.
Okay. See, whatever you are saying, no, like I'll agree that because the when we are implementing the flops, we will be using the NAND gate or the NOR gate. But to store the data, actually we need the sequential circuits. So here the universal gates are nothing but the NAND and the NOR gate. The application is like
Simple
you
to
can
complex circuits.
yeah. Yes, someone is saying something.
Yeah.
Yeah, please go ahead.
It is used in the designing of simple circuit to the complex circuit, ma'am.
Okay. See it's whatever you are saying, it's 50-50% correct. I'm not saying I'm not denying about that. Simple is like why we need the universal gates means with the help of the NAND gate and the NOR gate, you can implement any gate. So it means that whenever suppose consider that you want to implement the AND gate. Suppose you need the logic of the AND gate, but you don't have the AND gate. So what we can do with the help of the NAND gate, just add the NAND gates in your design. So with the help of those cells, you can implement anything, right? Whether you want to make it as a AND gate, whether you want to make it as a NOT gate, anything. So that is why we are using the NAND gate and the NOR gate. When you compare the NAND gate and the NOR gate, we will always prefer the NAND gate, not the NOR gate. Why? I'll tell you like in the next sections. So the simple is like with the help of the NAND gate, you can implement any gate. That is the application. Suppose consider that you need the your design. Suppose consider that you are doing something, you need the operation of the AND gate, but you don't have the AND gate. So that is why just simply insert any like AND gate, whatever you want the logic, you can make it. Don't be so complex. Just understand this one. With the help of the NAND gate, we can implement any type of gate. This is so that's why we will be using these gates in our design. Any doubt in this one? If you have any doubts, please ask the question. No worries. Any doubt in the NAND gate or the universal gates? Why we need it exactly, you guys will be understanding once you get into the PD. So don't think much about this one. Any doubts?
No.
Okay. Next, we'll move to the NOR gate. NOR gate is also universal gate. So it needs the two inputs and it will provide only one output. So here it will do the inverted operation of the OR gate. So here you can see that this is the symbol of the NOR gate. This is the symbol of the NOR gate, or else you can represent this one also. This NOT represents the NOT gate. So here you can see that whenever the inputs, here it will be having the 2 inputs, it means that it will be having the 4 possible condition. If the input is 0, 0, what will be the output of the OR gate here? What could be the 0, right? So the 0 will be inverted. So what you will get at the output?
1, 5.
1. Yes. So when A is high, B is low. So when A is 1, B is 0, what will be the output of the OR gate?
0.
A is 1, right? So the output of the OR gate will be 1. This will be inverted. So here what you will get at the output? The 1 will be inverted. You will get the output as
0.
0. When A is 0, B is 1, what will be the output of OR gate?
1.
1. 0 plus 1, it will be 1. 1 will be inverted. So it will be having the output as
0.
0. Yes. When A is 1, B is 1, what will be the output?
1.
1. So it will provide the output as
0.
0. So here you can see that it is providing the output high whenever both the inputs are at a low. The rest other condition, it's giving the output as low. So it is exactly reverse case of the or the complement of the OR gate. So the OR gate will be high in if any one of the input is at a high. So here in this case, if any one of the input is high, the output will be 0. So here this will be the exactly reverse case of the OR gate, right? Or nothing but it's a complement of the OR gate. Here you can write it as this. Here the expression will be A plus B, right? It is a complement of the OR gate. So this will be A plus B whole bar. This will be the expression of the NOT gate. Any doubts in the logic gates? What are logic gates? What are the inputs? What are the outputs? Why we need the logic gate? Any doubts?
Ma'am, in OR gate 1 plus 1, sometimes we will write 0 with carry of 1
That
in
is,
arithmetic.
yeah. See, that goes to once when you go to the adder. So that is not like a 1 plus 1, the carry will be 1. That is a addition. So that's why I told you guys OR gate is a logical addition operation. This is a logical addition. Whatever you are saying, no, that will come into the like adders, right? There also I will explain you like how the thing will be like 1 plus 1 as a 0. The OR gate, it will perform the logical addition operation.
Okay.
Okay. Apart from that, any doubts? If you don't have any doubts, then I'll move to the implementation. Here you guys can see that these are the implemented. This is how it will work as a will show you like. You have the NAND gate, but you want the NOT gate. So you want to implement, right? So how you are going to implement? I have the NAND gate here. This is a NAND gate. What is the NAND gate operation? This is having a 1 input A and this is having a B and this will be the Y. What is the expression for the NAND gate?
AB bar.
Bar.
A, B, bar. So nothing but when the output will be high, when
नहीं
the
पैदल चल
output will be high, for the NAND gate, when the output will be high.
when one of input is high.
When both the inputs are at a high.
Ma'am, NAND या AND?
Inputs
NAND,
are at
NAND.
high, output will be low.
For NAND, when
High
one
output
of
will be low.
input is high, then the output is high.
Okay, if both the inputs are at a high means?
Ma'am, its output is
Low.
low.
Okay. So that
But
you guys have
the
a
ma'am, you as you write, the expression is wrong. A dot B is it should be.
see, either you can write this also. Okay. Either you can write it as a A dot B or the AB, that's fine. So here, this you want to make it as a NOT gate now. So for that, how you are going to do? I have the NAND gate, but I need the result of the NOT gate. So for that, here this is the NAND gate, right? This is the NAND gate. So here, what I will do here, I will short both the inputs and I will provide the input here. These are the, don't confuse that you have only one input. Here you have the two input lines. I have shorted both and I have provided one input. Nothing but here also I am providing A and here also I am providing A. Here also it is A and here also it is A. Okay, this what you will get that the output here
A bar.
A bar.
A bar. Now it is working as a NOT gate. Yes or no?
Yes, ma'am.
Yes,
Got any doubt in this one implementation? Any doubts in the implementation part?
No, ma'am.
Okay. If you want to implement as a AND gate, now we want to make it as a AND gate. How you are going to do? This is a NAND gate. This will be A into B. What is the expression for AND gate? This will be A into B, right?
Yes, ma'am.
So here what you are getting, it will be A into B bar, right? So what you want me to do, like in order to get the AND gate operation?
Not gate has to be replaced.
It should not be replaced, just add a one NOT gate. But how will you add the NOT gate? Which NOT gate? Directly will not add the NOT gate, or you will use the NAND gate as a NOT
NAND
gate?
NAND based not gate.
Yeah, NAND based NOT gate. So here this output should give this as like this. So here it will be like A into B whole bar will get cancelled. You will get the A into B.
Okay.
Okay. Next, you want me to use the as a OR gate. So how you will get the OR gate, because you need the A plus B, right? But you have the input as, sorry, NAND gate. This is A, this is B, this is a NAND gate. So how will we implement the OR gate? How will implement?
Here we need three NAND gate actually.
Yes.
So the first two NAND gates will be shorted like in NOT gate, and
Correct.
further the output of both the NAND gates will be given as an input of single NAND gate.
Okay. So for this one, you guys need the, with the help of the one or the two not NAND gate, you won't be able to implement the OR gate. Why? Because we need the A and the B, right? So for that, just make use of one NAND gate for the one input. So short both the input lines here. This will be A. Use another for the B. This both will be shorted and this will be B. So here what you will get the output here, this will be A bar, right?
A
And
bar
this will be
and
the
B bar.
B bar. So give these two inputs to the
Inverter.
NAND gate. So here what you will get as a bar into B bar into whole bar. So here this will apply the which
DeMorgan's
De Morgan's
DeMorgan.
theorem. So here split the bar, A double bar, the into will be replaced with the addition. This will be B double bar. So bar double bar will get cancelled. You will get as A plus B. So to implement the OR gate, you guys need the 3 NAND gate. So this is how you are going to implement. Any doubt in the implementation part?
No, ma'am.
Okay. Any doubts in the logic gates?
No, ma'am.
Similarly, can you give, yeah, tell me.
No, ma'am. No doubts.
Okay. Similarly, with the help of the NOR gate, please implement all the gates. Here, I have not implemented XOR and the XNOR. Please give a try. If you are not getting, I'll explain you tomorrow. I just wanted to know you guys, like whether you guys have understand the concept or not. So that's why I'm giving these assignments. And please implement all the logic gates with the help of the NOR gate. And also XOR and XNOR with the help of the NAND gate also. If you are clear in this one, like I'll go to the next topics. Otherwise, I will have a revision and I'll move to the next topic. Any doubts? These notes will be provided for you guys. It will be having in the drives. So I think the management will provide you the access for that one, those who have registered. If you want to make a notes or if I'm going fast means please interrupt me there itself and so that I will be knowing. Any doubts so far?
No.
Okay. Please do the assignments and if you have any queries, please let me know about the queries. So we'll take the queries, do the assignments and we'll see you for tomorrow's session. Any queries?